In this video, we want to find talk about the derivatives of inverse trig functions. Now, to do that, we're going to have to use implicit differentiation. So the first thing I want to do is I want to go back and I want to review a little bit of implicit differentiation. And if you remember what implicit differentiation is we're going to take the derivative, we're going to find dy dx of some equation, but that we can't solve it for y. We don't know what y is. We only know y is some implicit function, some implied based on the equation. So what we're going to do is we're going to take the derivative of both sides. So if it's just an x, as in x cubed, that derivative is just 3x squared. If we take the derivative of the part with a y, we just do chain rule. Derivative of the outside, which is cosine, inside stays the same, times the derivative of the inside, which is 2y, times the derivative of y. So that's actually like three parts. Sines on the outside, y squared, and then the third inside part is y, and the derivative of that is just dy dx. We take the derivative, set equal to 7, and the derivative of 7 is just 0. The next thing we need to do is we need to solve this for dy dx. So we want to solve this for dy dx, and we can kind of see what's going to happen. This 3x squared is going to go to the other side as a negative. And all of this, that is times the dy dx, we're going to divide by that and get cosine of y squared times 2y. So there is my implicit differentiation of this equation. So we need to use this technique to find our inverse trig functions. Now, before we jump into that, let's just refresh our memory on what inverse trig functions are. If you remember sine, we can put any number into sine. You can take the sine of any number. Now remember, we're talking radians here. And your range, what you always get out is -1 to 1. Always. Now, when we find the inverse trig function, remember we got to change things a little bit. If we use sine on -infinity to infinity, we get our wave function. It's not 1 to 1, so it doesn't work. So we change this to be from negative pi over 2 to pi over 2. Therefore, our domain of inverse sine is -1 to 1. And our range is negative pi over 2 to pi over 2. Now, to help you remember what that means simply on the calculator, I'm going to put our calculator into degree mode. We understand degrees better, so let's understand what this means. If I take the sine of 30 degrees, and then I take the inverse sine of that answer, I get back 30. If I take the sine of 85 degrees, and then I take the inverse sine of that answer, I get 85. Now, I cannot take the inverse sine of -2. I get an error. Because remember, what that's asking, what the inverse is asking is, if you remember it this way, the regular sine function is the sine of some angle gives you the y coordinate. When I do inverse, I'm taking the inverse sine of the y coordinate, and it's going to give me an angle. So if my y coordinate is 1/2, inverse sine of 1/2 says the y coordinate on the unit circle is 1/2. What's the angle? 30. But the problem is the sine of 150 also has 1/2. So if you remember, when we looked at this with our unit circle, back when we were first doing trig, it only gave us certain answers, right? We only got answers from pi over 2 to negative pi over 2, and it gave us answers in this quadrant. We couldn't get answers over here because then it wouldn't be 1-to-1 and all that kind of good stuff. Okay, so that's just a refresher of what this inverse sine is. Sometimes it's also called arc sine, is another way of phrasing it. So if we look at something like this, inverse sine of square root of 3/2, that's asking what angle has a y-coordinate of square root of 3/2. So where is our y-coordinate of square root of 3/2? That is right here. So my angle is pi/3. If I said, what is sine of pi/6? That is, at pi/6, what's the y-coordinate? And it is 1/2. Okay, so that's kind of a quick review of what inverse sine is. Inverse cosine, everything else is the same thing. Now, what if we want to take the derivative of inverse sine? How could we do that? So I didn't give you a whole lot of room on your notes, so let me just go write this down here. The derivative of inverse sine is 1 divided by the square root of 1 minus x squared. Now just look at that for a second. We're taking the derivative of a trig function, and we get something that's got nothing to do, or at least looks like it's got nothing to do with the trig function. It's 1 over the square root of 1 minus x squared. Now, let me see if I can kind of prove to you what that is. So we are looking at the function inverse sine. Now, if you remember what that means, inverse sine, going back to here, consider these two things right here. If I have inverse sine, I want to go over here. I get the sine of theta is the y-coordinate. So here, that is going to give me the sine of y is x. Okay. Now, let's take the derivative of both sides. Now, this is why we needed our implicit. Well, the derivative of x is just 1. Pretty simple. The derivative of sine is cosine y times the derivative of dy dx. And we're trying to find dy dx, so dy dx is just equal to 1 over cosine of y. But how do we get from 1 over the cosine of y to this radical? How do I get from here to here? Well, let me kind of prove to you how that's going to work. Let's go back and think about our unit circle, and I'm just going to look at the first quadrant. Okay, so if we're in the first quadrant, and consider what I had over here, and that was, let me write that down here. This is the sine of y equals x. So that means I have some angle y, and the y-coordinate of this point is equal to x. Okay. So if I want to find cosine of y, and the hard part is here when you're thinking of the graph, we're using x and y, even though this green line is the x-coordinate and this blue line is the y-coordinate, but we're calling it x and our angle is y, so try to stay with the notation. The question is, what's cosine of y? Or another way to think about it is, what's the length of this side? Well, if this side is 1, we know by Pythagorean theorem that the green side squared plus x squared equals 1 squared. Or more importantly, that this side down here is the square root of 1 minus x squared. So there is what the cosine of y is equal to. So if I take that cosine of y and I replace this with the square root of 1 minus x squared, there is my formula for the inverse of sine. Okay. And that's one we're going to have to memorize. There's two, just like we talked about before. There's one we're going to have to know. Okay. So we memorize that. We don't want to go through that whole implicit differentiation to prove it every time. We just have to remember that. So let's look at an example. What is the derivative of inverse sine of 3x squared? Well, our derivative of sine is inverse sine is 1 over the square root of 1 minus x squared. But by the chain rule, it's the derivative of the outside with the inside staying the same, times the derivative of the inside, which is 6x. So it really is the same kind of chain rule stuff we've been doing. We now just have a new formula for inverse sine, but we deal with the chain rule the same way, just this new formula. Now, if we want to look at the derivative of inverse tangent or inverse secant, we have these two. And once again, the big one to remember is the derivative of inverse tangent. If you want to circle that one, star it. The two that you have to remember are inverse tangent and inverse sine. We are not going to worry about the others. I'm giving them to you here so you can figure them out. Okay. Now, what about cosine? Well, I'm going to jump ahead in your notes here and actually get to those. Those here are our other derivatives. And notice that the inverse cosine, we really can write it as inverse sine. And the same for all the others. So we really don't have many that we have to worry about, just tangent and sine. And where these really come up is when we start looking at application problems and you're dealing with right triangles and SOHCAHTOA and those types of things, and you end up with these inverse trig functions when you're solving for angles, and we need to be able to take the derivative. So if you're given a choice that you can label something, for example, if I have some triangle and I want to find what theta is, and I have, 3 b, I don't know, m, and I'm trying to write my equation with those variables, I know the inverse sine. So I am going to say, well, the sine of theta is b over m. I'm going to write it in terms of sine, or I'm going to write it in terms of tangent, b over 3, and so forth. So you can use any trig function. These are the two we're going to focus on. So the ones that we have to remember, once again, is inverse tangent, 1 over 1 plus x squared. Similar kind of proof as the derivative of inverse sine, 1 over the square root of 1 minus x squared. All right, that is section 3.5. Here is all of the homework for section 3.5. This homework is due when we come back from break. So this is due on Tuesday, December 1st. The first half of the homework, this first line here, is just straight implicit differentiation. That is what we kind of did on Friday. This is the first part of 3.5, 3.5a, if you will. This second line is what we looked at today. This is kind of 3.5b. This deals with our inverse trig functions. Don't forget, once you watch the video and you look at the homework, don't forget to complete the lesson on Otis to get credit for having completed the lesson for today. And then once you do finish this homework, take a picture of it and submit it in assessments on Otis. And you need to do that before Tuesday, 12/1. I would encourage you to do this sooner than later. Don't wait until after Thanksgiving. Try to get it knocked off this week while this is all still fresh in your mind.